All right, welcome back everybody to the, I think, 5th episode now on the Daedalus upgrade project. And today we are going to be focusing on the electronics of our wonderful printer. So as you guys remember, the original electronics were a completely duet system. It had 24 volts and it was a pretty cool system in general, but I just did not like the duet experience. I thought it was a little bit, kind of outdated, and it just didn't suit well for me. So I wanted to Klipperize the entire system, and I had an Octopus Pro board laying around along with an extra Raspberry Pi. I know that seems a little bit weird to have laying around, but I just so happen to have one. And I know you can run Klipper on the duet system, but for whatever reason, my duet board wasn't cooperating with me. It's probably something I did. It probably works totally fine, but I didn't want to take the time to look at it if I knew that the system was going to work and I had it on standby. So as you can see, we have the Octopus Pro board here, and we have the 24 volts power supply. We also have the 48 volt power supply, which is just going to be powering the motors. And we have the RPI, its dedicated power supply, just so that we don't have to deal with any power supply issues, which might occur with this system. I've never dealt with it, but a lot of people have, and they recommend for the $15 that this 5 volt power supply is, just get it and install it. But yeah, that's what I've done. Another thing you might notice is that I took the motor assembly and I moved it over to the center for a couple reasons. One, I noticed that in real life, the model here I made before ever doing this in real life, and I just took a couple seconds and put it together just to see that everything would fit. And I noticed that the RPI would always hit the bottom of the motors, and I didn't like that. I decided to move the motors to the center, and haphazardly it also made wiring a lot easier, since they only have to come down just straight down the middle and then connect to their respective spots here. So that made that a lot easier. We also got the CAN bus items right here plugged in, and that is going to come down the right side here. So the path is that the CAN bus goes through the cable chain, comes out around here, goes down this right side, and then goes down this cable chain and comes over here. So yeah, this is a rough placement of the cable chains. I'm going to probably add a couple extra spots, maybe a cable chain here, and I think that's about it. So let's head over to the actual, the back of our actual Daedalus and see what we need to do there and what we've done so far. Right before we get into the actual build, I wanted just to show the 3D printing of some of the plastic parts we needed for this build. These are all the parts needed for like the DIN rail clips, and I found this really cool air channel for the stepper motors. That's really necessary. And then here is a little clip of me printing out all of the wire cable guides, because we are going to need a lot of them in a lot of places. So I printed some extra along with some other items that I found really interesting. PSU cover, and here's me satisfyingly breaking it off the bed. This is my favorite part of any print. Yeah, I want to show you this before I got done with the entire build. Okay, so I wanted to show you guys how to do the wiring, and I actually got this from an old 2.4 Seaboard kit that I had, and a lot of the wiring is the same. And this is how I learned how to do the wiring. Of course, this is all going to be on their GitHub, and all of their wiring has been updated for some more newer stuff. So the only thing that I did differently is that right here are the motor cables, and I had these two cables just go out to a 48 volt power supply, and I'll show that over in the real power supply, but I just wanted to show you guys that. Alright, so here is the actual printer all wired up now. Excuse the absolute rat nest that it is, but I did need to go through and just double check that all the wiring was correct, and I didn't want to clean up the wires before knowing that everything was going to be good. So some things to point out: I had to make new inlet cable wires, and they just kind of run down and they go down to this section here. So one thing I didn't show in the actual 3D printer video is that down here, don't know if you can see, but down here I've got a Wago
five clip Wago, so there's 3 of them. One's for neutral, the other one's for earth, and the other one is for live down here. And what that does is it just pretty much acts as like a big distributor, so I can distribute out all of the power wherever it's needed. A couple things that you may have noticed: I did add a fan. Oopsies. Let me. A couple things you may have noticed is I did add a fan over all of the stepper motors here. I'm using the 5160 step sticks, and I personally don't like to use them too much because they always run hot, and I never really found a good cooling solution. So I looked on printables, and I found that this one, it fits my board perfectly. So a note is that if you're ever using 5160 step sticks, always put a fan on them no matter what. So I have this fan running at 100% all the time, or at least that's how I wired it. I'm not sure exactly because I haven't turned it on yet, but I have it going at 100% all the time, just so that it never gets hot. With these 5160s, if they ever get hot, they will just turn off, and then you might lose motor A or motor B, which would suck. The other thing to know is that that can be irrespective of the voltage. So even at 24 volts, if you have it running at any decent current, it will overheat, so you need to cool them down. So there's that. Here's the wiring for all of the board stuff, the RPI stuff. I did add a heatsink here with a nice little Noctua fan so that it's super quiet. Kind of useless considering that this thing is going to be super loud. And another thing that I'm going to do is I'm going to put 2 big, let me see if I have them. So I have these old Noctua fans from an old PC build that I have, and these are 140mm fans. I don't really know what to do with them, and nobody really wants to buy them. So instead of just throwing them away, I'm going to modify the back of the enclosure just so that they sit like right here, right over both of the PSUs, since these coils on the PSUs here get really hot, and of course I don't like that. So they probably are totally fine as is. They probably don't need a fan, but you know, I have them, might as well. And I'm going to modify the enclosure over there so that that works. Yeah, so that's pretty much it. I guess the other thing to talk about is Klipper, and how are we going to get Klipper installed. So before I even wired all of this up, I took the board and I took the tool head, that's right over there, which is the SP2209, and I installed Klipper onto the board, which was really easy over USB-C. And I might show a clip about a couple things, but that was really easy, and you just got to follow the Kiowa guide, and it'll show you how to process an image for the RPI, and then it'll show you how to install Klipper onto the main board, and then you can install Klipper onto the tool head and get all of those UUIDs that you need. Once you've got that installed on the tool head, you will need to have it hooked up to a 24 volt power supply and the CAN connection for it all to finalize the Klipper install. There's like a little section at the bottom. It needs to be plugged into the actual board so that the board sees it and not just the RPI. So I'm going to link the esoterical guide for installing the Klipper. That makes the guide so simple. I say before the esoterical guide ever came out, I was trying to do CAN bus, and it was so hit or miss trying to find a YouTube video that worked. So very happy that guide exists. I'm definitely going to link that in the bottom. But yeah, this is pretty much the entire system all wired up. It is pretty late at night, so I am going to do the first turn on tomorrow morning and show you guys all of that. So wish me luck. I hope this all goes well, and no black magic smoke. So yeah, let's do it.
Something I also really wanted to show was how to get this board into DFU mode. I know it looks a little bit overwhelming when you see this page, and I'll link this page, the GitHub for this page in the description below, but this took me forever to find. I don't know why the documentation for the Octopus Pro V1.1 is kind of all over the place. It's like they made an original document, and then just instead of updating it completely, they just like listed out some of the changes. But this document wasn't there, and this was really hard to find. But one thing that you should know is that this little pin right here is your boot drive that you will need to set if you want to put the board into DFU mode, which is going to be really, really useful. This right here is the USB-C that you're going to use to power the board, and you are going to need to put a pin over, I want to say it might just be this boot reset. Yeah, it might just be this pin right here, and then you can plug in a cable right here, and you can finally upload Klipper onto this, which is very, very helpful. The next thing to know is that when you are installing all of your drivers, you know, specifically the 5160s, I have them, I think they're up here. You need to flip these drivers so that they go over one to the left, and you can see this diagram. So these two pins are, you know, there's 3 pins. These 2 pins are currently jumping VM and VN, which is going to get you whatever the power to the board is. So that's going to be 24 volts in our case. And then if you move it over so that it's jumping HV and VM, what that'll do is that'll use your motor power cables, which is going to be the 48 volts. So wiring in the power supply to this thing is really simple. You pretty much plug everything here into the 24 volt power supply. You plug in bed power into the SSR, and then you will need to put the motors straight from the 48 volts, and then you're going to need to do all of the line neutral and power cables. So I'll show this again in person in just a second. All right, we're getting up close and personal with the power supply. So this is the 24 volt power supply, and this is the 48 volt power supply. And I really wanted to show you guys how this is all wired. So if we go to right here on the MCU, like I was saying, these 2 points right here are for just the motor power. And the way I wired them up is that these 2 cables, you know, positive, negative, they just go straight to the 40 volt power supply right here. And yeah, this is just lined up negative, positive, and then you don't need any of the other points. And then yeah, you line up, or you power up all of the necessary cables, which are going to be line, neutral, and line, neutral, and earth. And that's pretty much it for cabling. I'm really, really passionate about cabling to ensure that everything is safe for you guys whenever you guys have to do it. Everything else, while it looks like a mess, is actually pretty well organized in where it's supposed to be in space. And a lot of it is just you know, bundling it up and putting it in together. So thankfully we have this part done, and everything is looking really, really good. So what we'll do is that we're going to clean this up and put them on the correct cables and make it look a lot prettier. So yeah. Okay, we have finally gotten this thing all wired up. As you can tell, look at this huge rat's nest of stuff. And I wanted to film the actual first turn on. So you can see here, oopsies, here is the actual switch. And in 1, 2, 3, we'll see if this thing blows up. Oh God. Fans are going on. Okay. Looks like it's good. Oh my goodness. No smoke. No magic smoke. Everything's turning on. Let's see if I can load up the page. Look at that. We got Klipper to show up. Nice. Wow. Okay, it worked out. I am very happy. Why are you so out of focus? But it looks like the printer is working. And it's making all this noise because I was using the bed as a cooling plate for another print. But looks like this fan is on 24/7. We'll get that to work. But it looks like it's working. Nice. Something that I've been really surprisingly passionate about is
this Pinda probe. So I have this Physik Pinda probe, and I think when I bought it, it was supposed to be just the new Super Pinda, but they sent me the older 4-wire Pinda, and this thing is just terrible, bro. Like, it was horrible. It would do 2 or 3 probes, and then, you know, it would be so out of whack, so bad measurements that it would tell Klipper to retry. And so one point would take like upwards of 10 to 15 measurements, with like every 2 or 3 of them being retries, which is horrendous. So what I did is I scavenged an old Super Pinda probe from a Prusa that I had, the same Prusa that gave me those little clamps we used on the bed, and we used that Super Pinda, and it's been amazing. I mean, it's amazing. It works wonderfully, and it's highly accurate. So if you guys buy a Pinda, buy one from Prusa. Don't buy any other probes, because they just are terrible.
All right, here we are. I just wanted to show Klipper working on the machine. So if you guys have never seen Klipper, this is Klipper. It's a very nice, useful web program to get a web interface for your printer. If you're not sure on how to actually get Klipper, what you need to do is go through the whole install process that was laid out earlier with the esoterical guide and all the other guides that I sent, or that I showed you guys. And then once you have your Raspberry Pi all working and all set up, what you'll need to do is you will need to go into your router's web page, and you'll see a specific address pop up in a few minutes. You know, give it a couple minutes, and like 5 at most, and you'll see a network line pop up, and then you'll just type that network line right into your browser, and it should show up. So this is the page. You know, you can go through and customize it however you wish. You can adjust how it all is laid out. You can see what's available, change the themes. Very, very useful. You can also just directly type in all of the information you need. If you guys have used Duet, you can imagine this is oddly similar. It's almost exactly the same, mainsail especially, to the Duet software, which is pretty cool. But a couple sensing things that I set up. So extruder, heater, all of that's working. The thermistors are working. There's no errors coming up. And the couple temperature things that I looked up are just the MCU for the Octopus, the temperature for the RPI, and the temperature for the SB2209. I wanted to show you guys just my printer config. So this is something that I just threw together really quickly. It's not perfect just yet, but what I did is I went through and reassigned all the items for our motors, and made sure everything works properly, and set the maximum limits. If you guys wanted to set the XY homing current, I think you'd have to do that probably in your homing print start guide, somewhere down at the bottom, right over here somewhere. I'm not sure how to exactly do it. I did it on one of my older printers, but it is a thing. I just wanted to show you guys. This is just the printer CFG file that I have. When you first install Klipper, you won't have this at all. You'll need to go find a config example, which if you just go up here, hit config example, see the type of printer you are. So for us, it's Core XY, and here's a general example. There's also tons and tons of other ones. If you hit all, you know, I think Big Tree Tech has one for the Octopus Pro 1.1, so you could go in here and see what the drives are, what the pins are, all of that sort of stuff. Voron has a really good one, and VZBot, RatRig, all of those kinds of printers have really good profiles that you can just look up and at least have a starting point. The biggest thing to know is don't ever just copy and paste someone else's profile. That is a surefire way for you to break your printer or break something unnecessarily. So yeah, double check everything, make sure it all is pinned out and correctly written. And the way you can look at that is just going through that document guide that shows all the pinouts of the board that you're using, and just double check it all, make sure everything is wired correctly. And then before you do it, the initial setup checks, and what you'll do here is just kind of run through their initial setups. The most important thing to do is right here, stepper buzz. So stepper buzz is super important, because what you can do is you'll just type in stepper buzz, stepper, and then the stepper you will actually want to check. So you want to check X, you can check X, and then you check Y, you can check Z1, Z, and then, sorry, Z, Z1, and Z2. And what this will allow you to do is it's just going to rotate, just like it says here. It'll first rotate clockwise and then back counterclockwise. And this is really helpful because it will not allow the motor to rotate fully, but still allow you to see whether or not you are wired correctly. And then you can go ahead and do the checks and changes in your profile before ever breaking anything. So this is very, very handy. I'll make sure to leave this in the description as well. All right, guys, here is the moment of truth. What we are going to do is do our first home, and hopefully it all works out. So let's try it out. Boom. Okay, X end stop works. Y end stop works. Let's see if the Pinda probe is wired correctly. Okay, it is. Oh. All right, wonderful. So something to note is that I am using the 5160 step drivers, and I really don't like sensorless homing on the 5160s. It's really, really inconsistent and not good. It ends up always ramming the tool head to the side of the extrusion. I have a fleeting suspicion that it's due to your homing current. Like, you need to change the current that it runs at when it does its normal movements, and the actual homing current needs to be of a way lower value. For example, if I have these motors running at 2 amps right now, when it homes it needs to be at like 0.6 amps or 0.8 amps, whatever the minimum is, so that when it hits the wall, it can feel the stall and then actually relay that back to the board. Otherwise, it's just going to keep hitting itself. And when it does that, it's going to overheat the motor driver, so very bad. Alright, so what we're going to do now is we are going to do a Z-tilt and see if it does it correctly. So the way that I figured out these points is that I took the normal trident profile and then I just moved the probe points to exactly where the lead screws will be, and pretty much just taught it like, okay, this is the location, wrote down those locations, and then did this lead screw adjustment. And you can see as we get over to the console, and as we're looking at the console, you can see it trying to retry. I did set the bed point to 0.005, and this was way out. It was by 0.5 millimeter. And I set the samples to 5 because it's going to be super accurate. It's taking an average of all 5 measurements, and so at each point it's taking 5, 5, 5. The minimum is really like 3 for a good average, but it's going to do this for just a second, and then we're going to see what it finalizes at. Alright, it just finalized the Z-tilt, and look at that, the tolerance is 0.005 and it did 0.002, so this thing is super duper straight. And this is great because what this allows us to do is that it sets up the perfect place to see if our frame is actually square. So this is something that I never checked when the Daedalus was using Duet. Didn't know it was a feature, it probably is. But what we can do now is that now we know that the bed is level. What we're going to do is we're going to probe the entire bed with the Pinda, and we are going to look at the height map and see if the printer is actually square. And this will make more sense as we're going about this. So next up, we'll do that. When it comes to the bed, so I had to shop around and look at where I could find a similarly made bed. We know that our bed is made by Mandela Roseworks, and they are really good at making ultra flat beds. I'm not sure if my bed is ultra flat or if it's just a normal flat bed, but I found an old Railcore 300 ZLT magnetic bed, which looks almost identical to the bed that we have. And it looks like we are trying to aim for just under 0.1 millimeters across the whole flatness of the bed. So that is going to be our new goal for the flatness of the bed. Around here, you know, anywhere between 0.05. Yeah, that would be phenomenal. And then on the high side, we could do 0.13. That should still be well within our printer's capabilities of doing a very flat surface. So all of that should be good, but I wanted just to set some sort of metric so that we know where to aim for when it comes to printer flatness. All right, everybody. So we finally did the height map on the entire printer. And as you can see here, it is 0.271, which compared to, if you remember the flatness that we saw on the Illustrator page, that is like about double the height, which, you know, if I had a magnetic bed, I could kind of understand and blame the magnetic bed, but this is pretty high. So what this generally points to, and of course, this was after our Z tilt, you know, this means that there's some sort of out of squareness with our frame, because we know that the bed should be around 0.1, if not less than 0.1 cold. So, you know, the way that you look at this is, one, you need to just to see where your 0 points are. So you need to look at 0 on the X and the Y right here. And this front 0 point right here, this will tell you the front left corner of your bed. And that'll show you that, okay, this frame is tilted upwards, or sorry, this frame is pretty much the inverse of this graph. So this bed is pointing downwards like this, so the frame kind of slants upwards like that, meaning that the front bar is either too high, angled upwards, or too low. And since we know that the gantry is like fixed in place, we can start there and start looking around at the gantry and see where the squareness of all the parts are. A great video to recommend is from this channel, 3D Printers and Whiteboards, specifically the RatRig VCore 3, How to Get a Square Frame. This video taught me everything I needed to know about how to square up a frame like this. This video is really great because it taught me how to use some really fine tools, and I ended up getting a couple engineering squares that he recommended, and that's what we're going to use to square up the frame. And so I'm not happy with this result, but we will keep this in mind. 0.271 millimeters of deviation, and we will have to look around at the frame. Firstly, though, there is a pretty big dip right in the middle. You know, this is a pretty noticeable dip of 0.2 millimeters. So let's look under the bed and see if there's anything possibly causing this. Dips under the bed like this might just be issues with the actual PEI sheet. You know, you can get a range of flatness just based on the PEI sheet alone, because the tolerances there can stack up. So let's look at the printer, let's look at some items and see what this is, and how we can change that up. So let's hop on over to that and check out the printer. Okay, so we are back at the printer. We're about to investigate the bed. And before we do any of the bed and structural bed, you know, sort of taking a look at any of that stuff, the first thing we're going to need is one of these. So this is one of the engineer squares that the YouTuber that I just mentioned recommended. And this is a single billet piece of tool steel that had been machined out. And if you look at its designation, it's 875-00. You definitely don't need a -00. A -01 is probably more than what you'll need, but it'll be helpful here because it'll help us square out the corners. So first thing that we noticed on our bed was that the bed was a little high. So if we know that this surface is flat and we know that this gantry is fixed, we know that any sort of high up and down reading has to be from the frame. So given that it kind of looked slanted upwards like that, and the only moving systems are our linear rails, I have a very sneaking suspicion that the linear rails are not straight. Aside from that, let's look at the bed. So like I was saying, any humps or dips that happen in the bed, generally the first thing you'll want to do is take a look at your actual PEI sheet. You know, is it perfectly flat? Are there any grooves or scars? This is just a old sheet I had on here, but you can see that there's a little bit of PLA here, but this PLA was dug into the material, so I don't have to worry about that sticking out. And the first thing you'll want to do is just look at the bed
see if the bed has any items that might be causing it to be lower or higher. And first thing you notice is that there is a channel right here for the top side thermistor. And I think what's happening is that the Pinda probe is reading right in between these two items as it's going across. So I probably need to start the reading out a little bit further so that it doesn't see this, and then it can kind of guesstimate on what's going on here. I will link a video below if you guys do want to use the top mount of this top mount of this bed. And the top mounts are really good for seeing what the actual bed temperature is, because it always takes a minute for the bed to heat up fully, and this will read a more accurate reading. So this is pretty cool, and you need to set up a little RTV. You need to use a little RTV to set this up. Not hard at all, but it's just one of those things that could be done. So up next, let's look at the bed frame and see what it looks like. So here we are in the front of the printer. Right here is going to be the linear rail for our fixed gantry. And this is the front corner that we saw that is most likely being lifted or improperly installed. All of which are totally okay. Like, it's one of those things you can just fix. And we just wanted to double check it. So the things we're going to need are, we're going to need this engineering square, and we're going to need a very sharp flashlight. You can also use your phone flashlight here. And I decided to take the bed off and move it onto the ground. The image is currently dark so that when I shine this flashlight, you can actually see what I'm talking about. And the way we're going to do this is that we're going to take our flat side, the one that doesn't have a knife edge, and use it up against the side that we're going to use as a reference. So right here. And we're going to use this knife edge as our measuring guide, right? And what we're going to do, get that right up into the corner. Oops. Get that right up into the corner. And we're going to shine a flashlight. And so we can shine the flashlight here. You can see that's, if we shine the flashlight here, that is about as much light should be coming through. And on the other side, you can see there's a good bit more light coming through, but not that much. If we consistently bring it, we can start to see there's a whole crap ton more light coming out, showing that this edge, instead of being level, is actually tilted upwards like that, which is allowing more light to come in. And what makes this super powerful for this is that it shows us that this is out of whack. So how do we fix it? That's the next question. Okay, so in terms of how to fix this thing, we just got to take this thing around, and we can see that we've got these two holes right here that show that allow us to actually access these areas. So what we'll need to do, unscrew these areas, and then carefully hold this engineering square right in the corner and push down this top extrusion, and then tighten these two up. And then we'll repeat this on both sides, and then we can see what the actual results are for our more leveled bed, and see if there's any other areas in the printer that need to be leveled out. Now, I know these front screws are going to be a pain in the butt to get out. They're probably going to have that red Loctite that we had to deal with in the first few episodes. So, if you guys are doing this as well, be very much aware that this is going to be an issue. So, yeah. Something I really wanted to show you guys, because I nearly had a panic attack, was, I untightened these screws and it wasn't working. And then I realized this is the little corner joint I was talking about. So what we'll need to do is unscrew this little bolt here and move it down, or just keep it loose, and then that'll allow us to move it down. And then we should be able to fully adjust this top extrusion and see what happens. All right, we're going to do that, and then we're going to look at the leveling of this entire printer and see what happens.
Okay, I wanted to show this after a bit of tinkering and using my engineering square. This is about the best I could get in the for the height map. So as you can see right here, the deviation is 0.137, which is right in line of where I wanted it to be, which is between 0.1 or 0.06 and 0.13. So this is a little bit higher than that, but this is really good. One thing that I noticed was that the frame was out of whack in almost a lot of the corners. So what I had to do is specifically for the gantry, is I took a pair of calipers and I measured out each corner of the gantry to be a set number. I picked 99.5. It was right in the middle of all of the screws, so I set that to be the height. I used the calipers and just tightened all of the 80/20 extrusions up to the edge of the calipers on each corner, and it got me this really nice flat profile. I also started moving around some of the bits of the probing points so that it didn't ever hit the edge of one of the plates, or it never landed on one of the screws. This big deep hole over here was because the probe was hitting the edge of the screw that held in the magnets, which was causing it to be a deeper reading than it really was. So yeah, that was one thing. But now we have a really good deviation, 0.137. That's amazing, especially for smaller areas where you'll be printing. It'll be super small. So yeah, this is super good.